another video. This time we are going to be looking at free body diagrams in physics. So we are looking at free body diagrams. This is way too big, so let's shrink that down a little bit. Let's go. 7. Okay, free body diagrams. Basically, you already know everything you need to know about free body diagrams. Basically, all free body diagrams is a picture that shows all the force vectors affecting an object. Okay, so definition, let's write that down. A picture that shows all the force vectors affecting an object or body slash body. All right. Now, oh, that should have been 20 as well. Okay, so that's the definition of a free body diagram. What does it look like? Well, it would look like a point in the middle. So you have a point in the middle that represents your object. And then coming out of that point, you would have a bunch of arrows coming out of that point to represent all the forces that are affecting that object or that body. So it would probably look something like this. So if I take my pencil and I come down here and I go, there's my center, and then I would have a force like this, a force like this, a force like this, force like that. That's an example of a free body diagram. The most basic one that we've been doing is you have a dot in the middle that represents your object, your body, your whatever it is, and then coming out of it you have gravity pulling down on it, and then you have the normal force pulling up on it. Can I put a arrow at the end of this one? I'll draw the arrow after. Okay, and then you'd have coming out of it like so. So you would have boom, right? Which means that this is our FG, this is our FN. Okay, and then we also did a couple examples where our FG was pulling down, and then we had two FNs pulling away from it. So these were like the two cores. So you have force of tension 1, force of tension 2, so on and so on. And then you had more complicated ones. So let's go through this one. So if we go back to my famous coffee cup example, if I have a coffee cup sitting on a table, the forces that are acting on that right now, there are only two forces acting on it right now. One that's going straight down from there, okay, and then that's your force of gravity, and then you have another one that is going straight up from there, which is your normal force. Right? Those are the only two forces that are acting on this cup, and therefore this right here is a complete free body diagram. You have the dot in the center represents, I didn't put a dot in there, let's put a dot in the middle. So you have a dot in the middle that represents your object, and then you have the force of gravity pulling down, and then you have the normal force holding the cup up. That is a complete free body diagram, obviously without the cup in the background. Now, the second example that we had was a more complicated two wires holding a crate up in the air. So here, where is your center of your object? Your center of your object is there. So you put your dot in the middle of the crate, and then you would say, okay, we're acting upon this crate. I have force of gravity pulling down on it. And even though the connection is up here, we were going to say that we have, we're going to say that we have a force pulling this way. Boom. I want to make sure it's parallel to that. And then we have another force pulling right Then we have make sure we have another force pulling this way parallel to that one. Right, so that is our complete distribution. That should be sitting, touching the dot in the middle. So there is our complete diagram, free body diagram that has the force of gravity pulling down and then two tension forces that are pulling up at different angles. Okay, and then we'll come back and we'll do actual calculations without numbers and all that. And if we slide down, we have an example of an airplane. So now we have a moving object. So if we have our dot in the middle that represents our object, we have a force moving forward. We also have a force holding it back, which is wind resistance. So we have a force holding it back, and then because it's an airplane, we have a lift force. I gotta keep remembering to do that. We have a lift force keeping the airplane from crashing to the ground, and then we also have the force of gravity that wants to pull it to the ground. Okay, that should be straight. So let's label all of these forces. Insert text box. Boom. So we have force of lift force. So this one goes with this arrow, and then we also have a force pulling it down. Oh, I lost my arrow there. Force of gravity pulling it down, and then we also have the force going forward is going to be your driving force, and then you also have this one, which is a force of friction with the air. So air resistance, right? So that's your tailing, and then let's bring that arrow back. So force of gravity is pulling down on it. So that is our complete free body diagram for an airplane, where there are four forces working on it: the engine propelling it forward, gravity pulling it down. All these lines should be touching our dot in the middle. Air resistance holding it back, and then the lift that is created by the engine flying straight up in the air. Okay, we should probably label all these other ones as well. So here we have force of gravity is down here, and then this is force of tension, tension 1, and then this one would be tension 2. Tension 2. All right. And the coffee example only had two forces to deal with. We only had force of gravity pulling down on it, and then the normal force holding it up, right? Normal force holding it up and gravity pulling it down. So these are three examples of free body diagrams. Boom, boom, oh, and then the airplane one had this one, this one, this one, and that one as well. Okay, now once we finish this video, you are going to make sure you do the questions on page 289. Okay, do all the questions on page 289 that deal with labeling these forces. So this one was Fg, F drive, F lift, and F. Awesome. So now let's go on to what happens if you have all of these forces working on an object, on a body. Well, you end up with something that we call resultant force. Okay, basically resultant force is what is the effect, what is the final effect of all of these forces acting upon the object or acting upon the body. So if you have multiple forces acting upon the body, what actually happens? What is the last thing that happens as a result of all of these forces? So by definition, resultant force is going to be, we call it Fr. That R should be small. Why can't I make it small? Fr is equal to F1 plus F2 plus F3 plus dot 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 F whatever. So depending on how many forces you have, the resultant force is going to be all of these forces added up together. Now, when we are doing this adding, we are dealing with vector addition. Okay, super important. And you remember that part. We are dealing with vector addition. Okay, not just the actual magnitude of the force, but also taking into consideration the direction. Okay, this is super important. We are dealing with vector addition. I'm going to make it right color there. Boom. Okay, what does that mean? That means that if you had multiple forces coming from different directions, you are going to have to figure out where these vectors are located before we can figure out the resultant vector force. So an example would be, let's go to boom. So there's a picture of one hockey player being hit by two hockey players. So if we turn this into our free body diagram, this hockey player is going to be the middle. And then this hockey player is getting hit by this hockey player who's a little off balance, so it's a fairly small force, like so. And then this hockey player is in full speed, full charge, so it's coming at the poor guy in the middle at a much greater force. Now, what is the resultant force that this player is feeling based on these two players? Well, you have to add these two vectors together to figure out what's actually happening with this, because they're sort of they're sandwiching this player. So they're both sort of heading in the opposite direction, not exactly. So some of the forces will cancel each other out. So what we do is we take this one, we copy it, we bring it down here. There we go. Okay. There's that one, and we take this one, we copy it, and we bring it down here. So we attach them together, except that's a terrible color. It disappeared. You can't see it anymore. I want to change colors. Shape outline, solid. There you go. So we have, let's change that one as well. Make that one, boom. So now we have the two forces acting upon it. So what you end up with is actually a force vector that goes like that. So this one here is your resultant vector. So this player will actually be moved in this direction, which helps this player because it's going towards the puck right here, because this force is that much greater than the force pushing him off the puck. Okay, so when we're trying to do resultant force vectors, we have to make sure we're doing vector addition, where we take the actual vector and we go tip to tail, tip to tail. Even if I had gone the other way, so if I had gone this way, if I moved it up here, for example, tip, and then this one to tail, I end up at the same place. So it doesn't matter if I start with this vector and I add this vector, or I start with this vector and I add this vector. I will end up in the same place. So for this player, it will be shifted, pushed that way to like where the orange arrow is, pushed that way. Okay, so your resultant vector is going to be that. So let's do the same thing here. So we have one vector going like this, and then we have another vector going like this. Let's make this one a little longer. Your resultant vector is going to be, repeat this one, boom, like this, red, and then this green is going to be your resultant vector. Okay, so this is your force resultant, and this is your force 1, this is your force 2. Okay, so the arrows go like this, like this, like this. Okie dokie. Awesome. So now, if that's a simple one where you have two forces acting upon one object. So if we go back to our lovely pictures over here, if we had a scenario where we have a sailboat out in the middle of the ocean, and there are different forces affecting that sailboat. So we have the boat. Oh, we need a dot in the middle, so this represents our sailboat. Okay, the boat wants to go in this direction. Boom. Make it a nice big heavy line. The boat wants to go in that direction, or it has the motor going that way. And we have the ocean current, let's say. The ocean current is pulling it in this direction. Okay? We have the ocean current pulling in that direction. Make it a nice big heavy line. And then we also have the wind. Now, these people aren't very good at sailing because the wind is going that way for them and not helping them at all. Okay, so there are three forces acting upon this object right now, this boat right now. So if I take that, what if I just copy it? Group it. Oh, group it. Group it. Group it. Oh, this is working out. Nope. Group it. Group. Copy paste. Ah, awesome. Now slide this down, out, down into a usable space. Boom. So here is our diagram, free body diagram. So we have the boat in the middle. The driving direction is going straight up that way. The current is going that way, and then the wind is pulling back on it. So let's say that our wind has force of the wind. The force of the wind is 2,000 newtons. 2,000 newtons at 210 degrees. Remember your coordinate system? And then we have the force of the drive, remember that's going forward, is at 8,500 newtons at 45 degrees. And lastly, your current, which is the water going backwards, no, the water going sideways, sorry, is at 1,500 newtons at 110 degrees. Yes. Okay. So I'm going to color coordinate these lines so that it's easier to see. So 210 degrees obviously has to be the green line. Can I make the word a different color? Okay, 210 is a green, and then the 45 degrees has to be black, and then therefore the 110 degrees has to be the orange color. Awesome. So if we are given this information and we have drawn our free body diagram accordingly to go with it, what is our resulting vector? Okay, in order to solve for this resulting vector, we now have to take our use of algebra and trigonometry, figure out all the angles associated with it. I can't do it on the Word document, so I'll go back to this one, slide it down a little bit. All right, so for our example, we had a force going this way, and then we had another force going that way, and then a third force, oh, a third force going that, no, that way. All right. So our orange force, no, our green force was 200. No, what was our green force? 8,500 newtons at 45 degrees. And our blue one was 1500 at 110 degrees. And our orange one was 2000 at 210 degrees. And then they want to know what is the resultant vector. So what we have to do now is we have to take each one of these vectors, break it down into its components in order to figure it out. Okay, we could take them as is, so we could take them like this, and then say, okay, I'm going to move this one tip to tail, tip to tip, tip to tail, tip to tail, tip to tail, and see where we end up. Okay, actually, we will do that. We will do that. So, Control C, copy, and then I'll paste it down here at the bottom. Control V, where did it go? There it is. We will do that. We will move it down so that we can check our answers to see we're even close mathematically and geometrically or drawing wise. Let's ungroup them. Ungroup them so that we can move it around. We can say, okay, boom. Oh, this one, let's move it down here. This one, let's move it up to the tip. And then this one, let's move it over here. So essentially, well, we don't need the object anymore. If we're doing vector addition, we don't need the object. So essentially, what we should end up with is this vector that goes like so as our final answer. So if I go there as a blue one, that should be our final answer. So right now we're looking at something close to the 9 degrees. Let's see if mathematically we get the same answer. Okay. If we choose to break up this one first into our two component vectors, so the x and the y vector. To find the x vector, because it is the horizontal is down here, it is going to be the cos of 45. So you go 8500 cos 45. The y is going to be 8500 sine 45. Okay, and then the blue one, same thing. Because 110 refers to this measurement is 110, so this measurement is only 20, right? 90, 20. So the x is this way, and the y is that way. So the x measurement is going to be the sine 20 times 1500. And then the y measurement is going to be cos 20 times 1500. And then you have our amber one, which is going to be down here. Now, because it's 210 degrees, we know that this is 30 degrees. Okay, the x measurement is going to be cos of 30 times 2000. And then the y measurement is going to be the sine of 30 times 2000. Okay, let's do some quick little calculations here. Let me grab my calculator to make life a little bit easier. Alright, let's start with the green lines. Cos of 45 times 8500 is 6010.4. And then the sine of that, oh, no, I don't want that. I want sine. The sine of that is going to be same thing, 6010.4. Well, obviously it's the same thing. It's 45 degrees. Duh, Chan. Way to go. All right. Then we go B. So the x, or the green line, sorry. Sine of 20 times 1500. Whoa, what happened there? Sine of 20 times 1500 is going to be 513.03. And then the y is going to be cos of that, cos of that, cos of 20 times 1500 is going to be 1409.53. Now, for the blue, the x value is going backwards. So this is actually a negative value, right? Because the x of the blue vector is going backwards. So therefore, it is a negative value. Don't forget that part, okay? And then we do the same thing for our orange line. So the x value is going to be cos of 30 times 2000. I feel like I've done 2000 twice. Did I mess up? No, I didn't. Anyways, is going to be 173.2. Again, this is going backwards, so therefore it is a negative 172.3. And then the y value is sine. Hey, what is it? It is sine of 30 times 2. Oh, 2000, not 200. Add another 0. Come on, add another 0. There you go. Is 1000, 1000, and then the cos should be 0.0. So get rid of this point. Okay, let's delete. Let's erase that. So this should be 1732. 1732. Now, for this one, the 1000 is also a negative value, okay, because it's going down, right? This arrow is going down, so both the x and y are negative. So our final resultant xy, so resultant for the x, we simply add up the three x's. So that one, and that one. So we have 6010.4 plus or minus 513.03 minus 1732. Give us an x value of positive 3765.38. And then the y value is going to be add up that with that and that. So we have 6010.4 plus 1409.53 minus 1000. And the final answer there is 6419.93. So if we create the two vectors there, we should have something that goes up 6,000 and then over 3,000 to end up with something like that. Which is close. Oh, yeah, because this is more accurate. The other one's not, right? So this one is because I just drew these random three lines here. So this should be our resultant vector going forward. Remember that we draw the picture of the ship. The ship was looking like this. So it ends up going, we wanted to go that way, but it's going to end up going that way a little bit. Okay, so now we can plug in the values of 3765.38 up here, and then over here is that, and then you can use that to figure out what your resultant vector is, and you can also use these two numbers to figure out the angle at which it is headed. Okay? Awesome. Now, with the resultant vector force stuff, I would like you to do page 291. The question's on 290. Nope, not 291, sorry. 292. Do the questions on page 292. Alright? So, I think we'll end there. I think we'll end this lesson there today. Okay? There you go.